Hello, hello, hello. Happy New Year. And last time I will see you back here for 2022. I'm about to hit the button to submit the very last star for 2022, which is of course day 25. Um, and afterwards, I want to explain how I finally solved day 16 and day 19. For both of them, for 19, I was actually missing both stars yesterday still. And for day 16, I was still missing the second star. And I've now gotten all three of those, and I will explain how I did that. I've opened a Reddit thread to ask for some pointers, and I've gotten them. I found out that I've been pruning way too many paths, and we'll talk about that, and how I adjusted the code accordingly. And for 16, I did actually look up how to do dynamic programming. I've done some research. Apparently, it's not too common that people did dynamic programming to solve this, and I was able to do it with BFS just fine. Funnily enough, for part one, BFS was faster than dynamic programming, but for the other one, it was the other way around. So for part two, I'm sticking with the traveling salesperson approach, and I mean, all of these are traveling salesperson problems, but I'm familiar with dynamic programming as a method to solve it. And for part one, BFS was a bit faster. So without any more delays, let's finally submit the very last star here. Um, ta-ta-ta-ta, and oops, we're done. You make a smoothie with all the 50 stars, and we have a full calendar complete. This one doesn't animate, unfortunately. If we go to events, we're now able to see all 400 stars. I'm going to post a tweet about this. I'm very excited that we got to see this. Let's just very quickly open all of these calendars. Spoiler warning, these are going to be things you potentially haven't seen yet. Don't open anything twice. We want to go all the way back and then we can compare. So this one had a little snow falling and a little Rudolph guided sled in the background. The next one was this beautiful antenna sending signals over the city. Then we had the amazing circuit board, which generates differently every single time. I'm really impressed by uh day or year 2027, I should say. I mean, look at this. This is amazing. It's a different circuit board every single time. I don't know how he does it. Maybe there's just a set of like 10 and I haven't seen that they duplicate ever. Then we got the year I got exposed to Advent of Code for the first time, so it's holding a special place in my heart. 4 years ago in 2018. Then we got the solar system oriented year 2019. In my memory, it was the most difficult one. Then we had Nessie, and of course, Safari is messing up the little animation over here. Maybe I should actually show this in Chrome, huh? That might make it a little bit more animated. I can just log in with my GitHub account. No credentials to be. You know what? Better be safe than sorry. I'm gonna black out my screen for this. Just signing into my GitHub account here. Two-factor authentication code, verified, perfect. Okay. Scene one. Yes, here we are again. So this one had this little hurricane coming in on the map, which is not the most positive Christmassy vibe now that I think about it. Then 2021 was this like dark sea, deep sea oriented plankton bioluminescence thing. Really chill, very beautiful. I really like this one. We all could use a bit of calm in 2021. And then this year we just got the forest and volcano pattern. Oh, look at this. There's a little animation. Oh, there's little like balloons or something. I guess Safari just messed it up. Well, okay, let's finally go over how we solved day 16 and 19. I'm going to start with 19 because that's was the one where we had the last stream about. So, in the end, what went wrong is I pruned way too many paths. I was pruning every single timeline. Um, so this is the method where it's all at. I was pruning all the timelines where I was not building a geode if other timelines at the current time step were able to build a geode, and that's wrong. Instead, what you should do is to check if the result of the futures method here, if the maximum amount of geodes that would possibly be able to be built at all is smaller than what we have previously seen in the amount of geodes. How do you get there? I came up with, I'm not sure if this is optimal, but it works. The idea of saying, okay, what if you take the like sum of numbers of natural numbers up to n, which is n plus n times n plus 1 divided by 2. And this will give you the number of robots over time. So let's say we have 5 minutes, you build a geode robot every minute. So at the start you have 0, then you have 1, 2, 3, 4, 5. And for all of these times, you're adding together these number of robots because that's the amount of geodes that you get at the end of the time. So if you, for 5 minutes, you build one every single time, you're going to have 5 times 5 plus 1 divided by 2 geodes at the end because every robot every minute builds a geode. And this is the time left because we can't build one right now. We can only build one in the future. So we're kind of saying, okay, we start with whatever n is. I think we start with 24. Yeah, so we start with 23, which is the maximum number of new builds. The time left with new builds, which means every single minute you build a new geode. That's complicated, but we use it right here when we say um, if the time left times the robots that we have, plus all the robots we could, all the resources we could ever have in the future, plus all the resources we have now is smaller than the amount of geodes that we previously found, then we return. We're not the optimum time path. We don't have a viable future path. And where do we get the max geodes from? Well, max geodes is simply the maximum for the current timeline, which is, so this is a very optimistic approach. This is a very pessimistic approach. In the most pessimistic timeline, no, in the most pessimistic outcome for one timeline is better than the most optimistic outcome for another timeline. That would mean that the second one can be pruned. And here we have the resources of the geodes that we have plus time left times the robots that we're currently. That's the one optimization that we have. This is the correct pruning. Now, the second optimization that we built in is to check the maximum amount of resources we could ever need. I messed this up big time because I was thinking, okay, how many resources could we need? And I was trying to find the upper bound by saying, look, we take the ore cost of everything, we kind of divide it by 2 on a whim, and we say we're going to build a silver robot every minute, and we're going to build a geode robot any minute, and we take all of those resources together, and we compute how many ore, clay, and silver resources that's going to take. And those are going to give us the max silver, max ore, and max clay. And these are going to be checked down here in the future, where we say if our resource has already reached the maximum level, we're just not going to build that robot anymore. So if our ore resources have reached the max ore, don't build another ore robot. If our clay resources have reached max clay, don't build clay, and so on and so forth. But Redditor later told me something genius that I didn't come up with, which is as long as you have the maximum resource requirement in ore as the amount of robots, you're set. Let's say a geode robot costs 5 ore. You will never need more than 5 ore robots, because every minute you get 5 ore. If the geode robot costs 5 ore, you can only build 1 per minute, and you're getting those resources every minute anyway. That would have been the correct way to approach this bound, but I've been able to get through in the end. This is not optimal, but it's sufficient. I think I'm running through both variants in 30 seconds now. And I was able to improve it a tiny bit more for part two by saying, because part two was really ramping up the time scale, and I came up with this method of saying, let's look at this. Yes, run blueprint. So the way I've been optimizing for part two is we say, okay, we are only able to build one ore robot and we see what we get to. Then if we increase the number of maximum ore robots, this is just a little hack I had to do for part one. Imagine it looks like this. Um, this is only for part two now. So if you can only build one ore robot, how much geodes can you get to? If we allow you to build two, how many can you get to? And if you just increase them one by one, you will always get more and more and more results because there's a certain limit, like a minimum amount of ore robots needed to get to the optimum result. But as soon as it doesn't get better anymore, which is this one, if the new best is the current best, then we're done. And this way, you really dramatically cut down the amount of timeline splits because there's only so many ore robots you can build. And ore robots are super common later in the timeline. You will never need them anymore. We're really cutting them out of almost all of the timelines. I thought this was a clever little like hack to improve the speed even more. Yeah, this is day 19. I'm not sure if somebody's watching this live. This is mostly just to finish up the YouTube playlist here. And I think that's all for day 19. So the three optimizations I was missing were make sure that you don't just prune if you're not building a geode robot when you can. Just make sure that you're never gonna be beaten by any other timelines that we've already found. So the upper bound of how many geodes you can have right now can never be lower than the lower bound of that of another timeline. That's one optimization. The next one is check the maximum amount of robots you will ever need, even though I didn't fully do this, I did this enough. And then for three, I personally optimized it, even though I haven't read this anywhere so far, by going through a number of maximum here it is. Number of maximum ore robots that you ever want to have to cut down on. But yeah, that's all. Let's move on to day 16. So here, you can do it with a BFS. Simple enough. What I'm storing here is for every node we have time passed, what node are we on, what is the current open flow, the open valves, and how much steam has been released. We also need to store which valves have been visited. This is the simple part. I think I've done this in a previous stream. Now, I said we need TSP to improve the time here. So it took me a long time to finally, understand how TSP works. Watch this amazing YouTube video. I'm going to put it in the comments. That really helped me out here. And ultimately, the necessary part was to not say we want to have the minimum distance of the path, but we want to have the max release of the path. So we're going to check for all of the potential paths that we currently have, which one leads to the maximum released steam. And for this max release, we're going to store the best choice. Now, the best choice is also more complicated than just, or is it actually? Now that I think about it. You know what? I think we don't need any of this crap. We can just store um, this. If possible release greater than this, then this is possible release. Huh. I stored so many different things. I don't think we ever need them. Now that I think about it. Yeah, there we go. Why did I think I would have to store so many different things? Um, well, let's see if we calculate anything unnecessarily. I don't think we do because we have new time, new flow. Yeah, this is all required to calculate the max possible release. Now, one thing I do have to do is um oh no. Never mind. Never mind. No, this is not gonna work. We do have to store all of this. Just ignore what I've been saying. Yeah, so we need to keep track of all of these different variables and resources that we unpack from the memo. The memo is like an array to check all the potential paths that you have open right now. And again, we need to know what is the current time, what is the flow rate that we currently have, and how much steam has been released. And now with all of these, we go through all the next intermediate steps and we check the next distance. There's a bunch of magic that we need to do in order to turn this problem, like, look at all this. There's like 50 lines of code that's simply turning the input that we have into an adjacency matrix. Um, Now, I do think we can make this a little bit shorter, like that. But yeah, pretty much we're turning valves into indices, which are integers. Then we create an graph matrix, adjacency matrix G. For the adjacency matrix, we go through every single start node. We calculate all the different paths, and we at the end add one to it because it's not just the distance, it's also 1 minute for opening the valve, right? So all of this is turning the input into an adjacency matrix, which can then be solved with the traveling salesman problem. Now, the important part is we only need to keep track of the nodes which have an open valve that will release more than 0 gas. The other ones are just distance to the next meaningful valve. And now part two is the interesting one, the one with the elephant. This we haven't solved previously. So this is something we already knew. This is where the fun is at. So one of the nice parts of the TSP algorithm I've chosen is that it came with this bit combinations method, which will give you all the binary numbers which have R bits flipped on in a bit length of n bits. So for example, if you give it, yes, dstore, that's exactly what I want. If you give it R equals 1 and n equals 3, then you might get back 1000001, right? Because there's 3 different ways to turn on 1 bit in a 3-bit number. And of course, these are all returned as numbers, actually. So it will not give you arrays or anything. It will just give you 1, 2, and 4, which is very neat. Let's say you want to turn on 2 bits, then it will give you this. Oops. I mean, it will just give you the thing inverted, which is the beauty of this. Because if you flip these, like 1 choose 3 and 2 choose 3 is the same. It's just what you choose inverted. Anyway, so this will return 6 and 5 and 3. Yeah. So with this in mind, this was very useful for this part of the puzzle because I'm splitting all of the valves except for the first one, which is always the starting valve, between the 2 different actors, right? So then we have a bit, like we choose half of the valves to be included in the subpath of one of the actors and the other actor. So because we're using global variables for a TSP, we have to set our global variables here. We change the indices for the flow array, and we take a subset of our adjacency matrix G, and we give it as inputs through global variables to our TSP method. Then we have the maximum um, released steam for one actor and the maximum released steam for the second actor. I guess I should rename this our LHS score and our LHS score. because I've turned the, like I've added the variable names left-hand side and right-hand side here. Yeah, but that's all there is to it. I mean, this thing takes like 41 seconds, I think. I did optimize it by saying, look, if we've seen these exact um, valves as selected for the one actor before, then we don't have to go through the reverse of it. If I give you the numbers 1, 3, 5, and I will take 2, 4, 6, it's the same result as if we swapped, because both actors are exactly the same speed and have the same um, properties. Yeah, that's all there is to it. Now, interestingly enough, here, you could just swap TSP and BFS. Literally doesn't make a difference. I think you can still see in my history. Yeah, when I'm running this with TSP for both parts, I get 41 seconds. If I run it with BFS, I get just over a minute. So the TSP was a tiny bit faster for part 2, and for part 1, BFS was faster. And I don't know why. Maybe it's because for the first part, we're usually not exhausting all of the nodes that we need. So the BFS can cut out a few paths by just returning early, right here, because this will not result in new features. Whereas the TSP will always look at all the possible node combinations, even if we're not even moving anymore, because our time has already run out here. If the previous time is greater than or equal to the limit, then we're not adding more, like, we're not going to change the time. The time will just be 30 for the first part, 24 for the second part. You get the gist, right? So this is why TSP is so much faster in the second option. And it would be faster in the first one as well if I had an idea of how to terminate this, but I don't. So yeah, that's day 16 and 19 finally done. For 19, there were the most things that I just missed, that I didn't think about, um, that I could have done more intelligently. And for 16, I think I didn't actually look at any hints at all. 19 was the only day where I looked at any outside resources to solve it. Um, and I think if I would have been more open-minded to the complexity of this day, um, because there's no rocket science here. Like, I came out with this on my own. I came up with all of this on my own. All that I read were like 2 sentences. Actually, I think I can show you what I read. If oh, this is beautiful. Hold on. I really like this Iris visualization now. I guess it helps if you don't have it in Safari. Oh no, Safari has the little balloons as well. Never mind. I'm just lacking patience. Okay. Um, let's go to Reddit and let's see what I've posted, because I have created a post. How do I see my own posted stuff? And profile? Profile. Yes. Okay, here it is. So what I read was, yeah, here. This guy is a genius. I didn't read this before solving it myself, but he is a genius. These two were what I read. You can build only one robot per minute. This puts a limit on the consumption of resources. I guess I haven't really properly internalized what it said, because I didn't understood this until reading what this guy said. But I did say you can build at most a geode every turn. This gives you some amount of geodes at the end. Yes. Anyway, I think the second line I used for both of my pruning approaches, and that was it. Let's see if I'm gonna do this again next year. I'm really tired. I learned a tiny bit about coding, and I learned a lot about time management. And you have a happy new year. and I hope it will be a good one. And I'm very grateful for Eric, the creator of Advent of Code, who put this all together. Happy coding, and have a good start of your week tomorrow. Bye bye.